Yeah, let's wait. Let's see if anyone else joins or not. Else we'll start at 6:02. Am I audible? Am I audible? Can you please respond? Hi, am I audible? Anuragha?
Yes, sir.
Yeah, so let's wait for 2, 3 more minutes. Let's see if anyone else joins. I'll start.
Okay.
Yeah, so let's start. Yeah, so hello everyone. My name is Rajay Mukherjee, and I will be taking this live session for NPTEL course on operating system fundamentals. We will be discussing the problems related to this week's part of the course that was completed. Along with that, we will be solving some problems. Along with that, we will be also going through the slides once again to recap what was being discussed. So, if you have any doubt, you can ask while I just going through the slides and all. So, let's begin. Yeah. So, so like previous week, we discussed how the OS uh, operates with the hardware as well as the user interfaces, like application program which we have written. So this week we again go through a bit of it. So uh, we describe operating system in a layered approach. So basically, the what does a layered approach means? So so if you are writing a program like a C program, you try to divide it into various modules. So one module will say just modules, or so let's say functions. You try to divide it into multiple small modular functions. So what is this modular approach helps? So the modular approach helps you in a sense that while you are debugging, or like you want to run a code, only small part of the code can be executed. So your focus can be on a particular part. Like each module will have a particular function and it will just operate on it. So Uh, Basically, a layered approach, you can say a similar way. You can view it in a similar way, that where the layer 0 is your hardware and layer n is your user interface. So user interface in your case can be your application program, can be something you are writing on the terminal, those kind of things. Layer 1 to layer n minus 1 can be various parts of the OS. Like we have seen that OS has some like it provides some functionalities for database processing, for communicating with the inner I/O devices, those kind of things. So there are many layered ways, as well as you have the system calls. So those that are way to represent an OS. So a typical operating system may consist of data structures and routines that can be in various layers or levels. So let's say you have written, let's take the example of a C code, where you have written a data structure for, let's say, hash. So a hash, or let's say you have written a data structure for tree. So the basic module of a tree, what it will be a node. So in a node, it will carry two pointers, left or right, and a data part. So that is the basic functionality. So on the bottom layer is your data, and the top layer is your node, which contains address to other two nodes. At the same time, the topmost layer will be your tree, which consists of various nodes. So that's a layered approach. Similarly, OS also has that kind of a layered approach, where there are lower level functionalities, then there are higher level functionalities, and so on. Okay, so in a layered approach, each layer is implemented with operations provided by lower level layers, just like a C program where you are writing a modular code, those kind of things. So advantage is your simplicity for construction and debugging, that helps in construction and debugging, like I said. Next, this so simplifies debugging and system verification. Just only you can to debug where the system has gone wrong. You can just check only one layer, and then the other layer, instead of just going through the all of it at a time. Okay. So any doubt regarding this layered approach concept? This is quite similar to how your C program works. Yes? Any question? Okay, so let's go to the next one. So microkernel structure. So microkernel system structure. So you know what is a kernel, right? So we have discussed it. So operating system is also known as your kernel. It is just a naming convention. So microkernel structure. So dividing your OS into very smaller segments. So into user modules, small user modules. So one is, let's say, your I/O system communication. Another is your communication with your databases or the main memory, those kind of things. So that is kind of what microkernel structure is. So communication between each module takes place in message passing. Message passing is a communication tool which will come across later when we are discussing processes, like how processes communicate between one another. So there we will come to this kind of IPC things, inter-process communication. So message passing happens there. So the benefit is basically easier to extend a microkernel. So you want to write your own kernel program, you just extend already set of program that has been written. Easier to port the operating system to a new architecture, more reliable, less code, those kind of things, and nothing as much important. So here I was saying, so this is your hardware, this is your application program, or let's say file system. This is your device driver. So these are your user programs or things, and there are message passing between these things. So application program wants to access the file. So you will it will pass message through this. So again, your device driver wants to access the file system, so it will pass message between this. Then your microkernels. So interprocess communication is one microkernel, memory management is one microkernel, CPU scheduling is another microkernel, and then there is communication between these microkernels and hardwares. So this is your typical OS, and just microkernel is a modular approach to extend the OS, nothing more. So many operating system implement loadable modules. Like I said that modules are basically so here you are seeing these modules, interprocess communication, micromanagement. These are basically modules, nothing more. So hybrid system, not much you require to go about. So this is your typical Mac OS or iOS architecture. So you have your application user framework, core framework, kernel environment. So your application is like communicating with all of them for various purposes. This is another architecture called Darwin system. Uh, then you have your OS like Android, which is based upon of your JVM. So Java framework it uses, Java virtual machines. So this is your typical Android architecture. If anyone of you are interested in Android programming, you will be familiar with this architecture: application framework, libraries. So so libraries. I hope you are familiar with the term called libraries. Like when you have done C++ coding, you would have come across these things called uh, libraries for string manipulation, libraries for I/O manipulation like I/O streams, string. Those kind of libraries are already present. So libraries are kind of same if you think about OS. So SQLite is for database, OpenGL is for graphical interfaces. Uh, Media frameworks are there, those kind of things. Then there are Android runtime systems, code libraries, virtual machines. Then debugging, operating system debugging. So if you have used a Linux system, you are like Ubuntu and all, so you will see a folder system is there called slash user slash log or those kind of things. So there you can file if you have any if your computer crashes or those kind of things happens. Let's say a program crashes, that a log file is generated. So what is a log file? If anyone has any idea what is a log file? So like, have you written C code, like a complicated C code you want to learn, but let's say it is not working properly. You want to minutely check it, like why the program is why the program is going wrong. So what do you do in such case?
For
Uh,
debugging in the log
so
files, we have the information.
yeah, so
Yeah.
what you try to do is you try to print some arbitrary outputs to check that whether this part of the code has been executed or not. What is the output in this small part of the thing? So log file is something like that. So when like you will see sometimes that you are using an Android device, and suddenly let's say you are using a your let's say Instagram app, and suddenly the app crashes and it says that log file generated. Do you want to send it like Instagram Meta for for identifying what is the problem? So those is a log file. So log file, it contains information of a running program, like what part of it has been executed. So one typical log file, if you are using a server programming, like if you are writing codes for server, you will say that you will get this server message always sometimes, like server started at port 8080, uh, receiving connections from IP address 10.10.10.10. So these kind of messages are generated, which are stored to understand how the program is compiling, or let's say it's running. At runtime, you can understand that how it is performing and what those kind of things. So debugging is one of such. It is helpful for debugging these log files and all. So if your error has been generated, you want to understand why the error is generated. So these kind of messages that are pasted in your log file helps in error, identify the error and for debugging. So it is basically a text file, nothing more. So another thing is code dump. What is a code dump? So let's say you have written a C code. Okay, for some reason the code, while you are running the code, it gets a segmentation fault. Segmentation fault, you know, right? Why segmentation fault happens? Suppose you are trying to freeing so you have used that term for pointer. So suppose you are trying to free a address location which is not available to you, or it does not exist. So that time segmentation fault occurs. So while that segmentation fault occur, it generates a dump. The dump file helps you identify where the like what is the mistake, uh, uh, where the code has stopped working. So it is basically an object file which has been created just to get understand for how up to how far that code has worked. So that is a dump file. So this so failure of any application generate a dump file. So also a dump file is generated when your operating system crashes or those kind of things. So those things are you will find in Linux in a particular path, like temp, like log user slash log, those kind of places you can find it. So this is a very practical way of handling error correction and debugging. Then this image you must be very familiar with. Like you, whenever you have, whoever of you are using your Windows laptops and all, you can do a Control Alt Del and go to your task manager. The task manager. Okay, this is a very old picture. This may be of Windows 10 or something, or Windows 8 maybe. But this screenshot tells you how much memory your computer system is now using. Also, it shows the CPU usage, percentage of CPU you are using. Then there is this page file usage history. So this page is something which will be introduced in the latter part of this course. So you can find out how many processes are this CPU running, how many threads are there in currently running. These kind of things you can know. So then it also tells you the size of your memory, currently available, what is the size of the system cache, those kind of things. Useful information, these things help you understand. Next, this thing for Windows, you have Windows Task Manager. For Linux, or let's say your Ubuntu systems and all, you have your top command. When you do a top minus p, yeah, Sneha.
Uh, there in the that screenshot, it is written that the processes are 50, but a one single processor can execute one process at a time, right? With multiple threads. Then how
No,
come
no,
the
no,
other
no, no, no,
four?
no. No. The one. Why would a CPU only execute one process at a time? then your program will not run right. How your laptop will be running? Your laptop
But
is running multiple processes. So
multiple processes, but like the time each process takes is very less, which is not.
yeah, when we will come to the like in the later part of today's video. So when we will come to the process part, you will understand how the process management works. So there is this thing called scheduling, process
Yeah, yeah,
scheduling. So process scheduling is there to do these kind of things. It is
no.
not
So
that one at a time a process will execution will takes place. Multiple processes at a time takes place. So this is your task manager on this how processes looks. Windows system sysgen is just a program which concerns specific configuration of hardware system and all. So sysgen is a typical tool which gives you the current configuration of the hardware system upon which like your OS is running. Nothing more to think about here. Then there is your booting process. So like this is a repetition of what we have taught when you are being taught in the previous lectures. So what happens when you boot the system? So basically your init program is loaded into your CPU from your ROM or EEPROM that is there. That is a small piece of code, and then your booting process start. So after the init process, the other processes required to run the OS gets executed, and then your program like boots. So that is being told here, bootstrap loader and all. So this that small speed of code is called bootstrap loader. Uh, okay. So any doubt regarding up to this, then we will go to processes, which is the main part of this today's session we will cover. Yeah, so let's, yes,
I have a doubt.
yes,
Uh, I have a doubt regarding this bootstrap loader is present in the EEPROM of the CPU.
yeah, yeah,
So when the power is on, this bootstrap loader loads the init program that is present somewhere, like maybe in the hard disk.
yeah.
That
No, no, it is stored in the, yeah, those kind of things, like those program takes it from your ROM, that is hard disk.
okay. So init program is present initially external to the CPU, and the bootstrap loader is in the EEPROM. Is
Yeah,
that?
yeah. Okay, so let's come to the what is the process. So we have discussed this term quite a bit. So what is the process? Process is basically a program in execution. So when you are running a code, a simple piece of your code, it becomes a process. So suppose you have written a hello world code. So when you run it, uh, so one thing is that like you will ask me that how can I, so I'm running a code, how can I notice how like what is it, where is the program running, where is my program running? So one simple piece of exercise you can do is you write a code and let the code run like this. So it prints hello world, but one hello world like let's say every 10 seconds after. So every 10 seconds it prints a hello world. Okay, so you run the code. So you open a parallel terminal and you do a top minus s. Suppose the object file which you have created for your C code is called, let's say, a.out. So when you do the top, you will be able to see the process ID of the program which you are running. So that is what a process is, program in execution. So program is a passive entity stored in a disk, whereas process is active. uh, Execution of program, you can run it using a CLI. You can use a GUI, mouse clicks and all. One program can have several processes. We'll come to this. So a process is more than a program code. So what are the things that are present in the process? Let's discuss this a little. So a process will have a stack. The process will have a stack, a heap, a data, and a text. So what is a text? So the program which you have written, that is the basically the text. So what is the data part? Data part, it's basically the values. Let's say it needs to uh, it needs to use for initialization of its variables and all. Like you have written a program. What is a heap? When you are writing a C code, you may have used this term called malloc and calloc. So that is the piece of memory from which your program can access uh, to use the dynamic piece of memory. That is basically your heap. And then there is your stack. So why is stack needed? Why is stack needed? So so your stack is needed basically uh, when you are running a program. Let's say your interrupt is occurring. So you know by this time you know what is an interrupt, right? So so an interrupt occurs. So, so when an interrupt occurs, you need to use interrupt handler, right? So at that time, what happens? So whatever process or program you are running, you need to stop it and you need to execute the interrupt handler. So how do you stop it? So you need to put the context of your process to some place. So at that time, the context is being stored in your stack, right? So that is how why stack is required. As well as that, there are other few parameters that are in your uh, process structure. So one is program counter, another is registers. So registers, you know, registers, CPU registers, whatever the registers your program will use, that is your registers. And another is program counter. So you know what is a program counter, right? So you have gone through your COA course, like computer organization course. So in that thing you are addressed like uh, let me just draw it once more. So your program is basically, so let's say you have written a code, void main int x y z is z equals to, let's say x equals to 3, y equals to 7. Let's say you have written x z equals to x plus y, and let's say you are printing z. So this part is converted into your assembly code, right? So any programming code is like is converted into your assembly code. So in assembly code it will be like this: x value is 3, y value is 7, z value is x plus y, and then there your print. So this is one. Uh, so 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 your processor, that is the CPU, uh, has this concept called load and store. So basically, uh, your this value, this is your program part. So these instructions, which are called basically instructions, the instructions and the data are both stored in main memory, right? So when you are executing the code, you have to load this statement from your main memory, then this statement from your main memory, and then this statement you need to execute. So at the first, your program counter is here. After this, so after this is executed, when we are executing this statement, your program counter changes to this one, and when this one is executed, your program counter changes to this one. So in a sense, program counter always points to the next line of execution in the chain of command, in your chain of instructions that are being executed. So that is why program counter is used. So similarly, your process has these kind of program counters to keep in check up to what part of the code has been executed. This is your process structure. Let me ask you a question. Can a program P can a program P can a program P have more than one process? Can a program P has more than one process at a time?
Yes.
Yeah. So you have written a program P, and let's say program capital P, and let's say small p is your one process, and another p2 is another process. Very practical example is you can open here you can open two sets of Microsoft Word at the same time. So basically it is the same program, but there are more than one process, right? Next, so why? So basically program is your process is your process is program in execution. Now we know P1 has its P1 has its P1 has something we call identifier. So PID1. So process identifier. So basically everyone has a name. You have a name, I have a name. So so to identify your processes, like what process is this, who is creating this process, who is that. So every process has an identifier attached to it. Just like everybody has a name, process has a own identifier. So process has an identifier which is attached to it. So process P1 has its own identifier, uh, PID1. It has a code area, let's say C1. It has a data area D1. It has some registers value phi1, and it's some program counter value, let's say XYZ. Now say this P2. So will P1 and P2 have same identifier?
No.
No. So it will have a different identifier, PDI2. Next, will C1 and on, let's say, C2. So will there will be two different code blocks. C represents code. Let's say C represents code. D represents data. Phi is your registers, and XYZ is your program counter.
Like if there is a addition and subtraction in a same program, then the code will be same, which it will refer
No, no,
to.
no, no. So I am
Like
saying
that.
there is only one program P, and it has two processes P1 and P2. So basically, consider the Word, MS Word. You have opened document 1, you have opened document 2,
The
right?
code will be different.
Uh, no, Word is the same program, right? You are running the same program. So code will
The
be same.
main program you are saying.
No, no, no. Let's say MS Word. Consider the practical example, let's say MS Word. So you are opening file 1 and file 2. So what is the program you are running?
Opening is same, but the fiber data will be different.
Yeah, yes, correct. So code area will be same. So the example which we are giving is that, let's say you have Windows Word program, Windows Word application. You open with it at the same time text file 1 and text file 2. So what happens in that case? You have two different processes. Process ID will be different, but the code will be the same because the same application you are running. That is MS Word. So uh, the code area remain same. Now data, just as Sneha said, the data will be different because you are opening two different files. You are opening a file F1 using program P, and a file F2 also using program P. These are two different files with different contents. So the data will be different. Similarly, the registers will also be different because these are the contexts which are required, which are user level contexts. We'll come to these contexts, what are these contexts and all. And this program counter will be also different, right? So even though Microsoft Word, you are opening the same applications twice for two different files, to open two different files at the same time, the process ID will be different, the data section will be different, the registers and the program counters will be different, but the code will remain same. That is our crux of uh, how a process looks like, how a process control box looks like. So any doubt regarding this? So you know, right, where from where you can get the slides and the videos.
No.
No. So 1 minute, I'm showing you. So you will go to your course operating system fundamentals, and there you will find this tab, problem solving sessions. So here you will click on it and you will get this. So here you will find all my videos and presentations which I am giving. Okay, so there you can get it. Now it is been uploaded on the NPTEL website, so you can easily get it. So here is your how process works and how the contexts are there. So let's get back to the this process thing, right? This we know. Now let's come to this, how a state occurs. Let me check here. Yeah. So here is your process state diagram. So first a new process is created, and once the process is created, it is admitted into this ready pool. Now a scheduler schedules this to the running state. What is what do you mean by here scheduling? So basically, in the ready pool, there are lots of process that have been created are in this ready pool. Pool in the sense it means, let's say, a group. So there are a group of processes here. Now the CPU decides, the scheduler, the CPU, the OS, this OS decides uh, which of the next process will be executed by the CPU. It decides. There are some fundamentally algorithms are there on so why a particular process will be selected. Let's assume there are some priorities. So for each process there are some priorities associated with it. So based on that priorities, the OS selects it and puts it into the running pool. From the ready pool, it goes into the running pool. Now, let's say an IO event occurs. So if an IO event occurs, it comes back to the waiting pool. When in the waiting pool, it performs in IO activities. Let's say taking input from the keyboard and all, and then goes back to the ready state. In case of an interrupt, it directly saves its context. Context in the sense is the stacks, the data, the heap. Those things are stored and they are saved in some, let's say, a table, and they are put back into the ready state. Exit following when the program is completed, it exists and it gets terminated. So this is your process state diagram. So this you need to remember quite well, like how processes and all happens and those things. So any doubt regarding this, you ask. Like this diagram is a little complicated, but this is how it works.
Like in the lecture, professor he was saying that in the ready state,
Yes.
in the main memory, the process is taken to, like, the process is in the main memory, and from the ready state it is waiting to be assigned to the processor. So once the operating system assigns it to the processor, it goes to the running state.
Yes.
And there is this scheduling thing happening. So I was just wondering that when they are putting it in the ready queue, which they are saying that ready queue is in the main memory itself, or that queue is in the processor itself, like where
No,
is
no,
the
no.
queue?
Okay. So let me just uh, expand this diagram. This is a very small diagram, but there are much more states than this. Okay, so let me show you another piece of diagram which I have prepared for this. So look at this. Is this visible?
Yes,
or should I?
please magnify it a bit.
Yeah, so I will just a little bit magnify it. Okay, so this is your uh, this is your process diagram. Okay, so this is your fork is process creation. So this is your state of process created. Now here two things happens. If there is enough memory, so if it has there is enough RAM which can, so basically each process is associated with some memory, right? That from that Windows task manager view, you can see that every process is associated with some memory. Okay, so if there is enough memory, the process gets taken into this ready state. If there is no memory, it is put into this secondary memory, not your main memory. That means your hard disk. There is no memory space available. Okay, so both things happens. So your confusion was in where state it lies. It lies in both spaces. It depends upon how much memory is there in your system. Okay, now uh, here your scheduling happens. That here is your let's let's think this is your running state. So in running there are two modes, user mode and kernel mode, right? So this is your running state. Now here the scheduling happens, and here is your kernel running state and user running state. When there is an exist, it becomes a zombie. So zombie is another process. Zombie is a process, let's say, okay, zombie will come to later, but let's say it's when the program is killed and its parent is available, so it becomes a zombie process at that case. But uh, it terminates. Let's think about it. It terminates. Now, user running mode and kernel running mode, these jumps and froth either when depends upon the system call and all. Now here is a sleep. So this sleep occurs due to that IO processes. So whenever there is an IO part, it exists into this waiting state. It goes into this waiting state. When it's done, it goes back to this pool chain. From the ready state, it goes back to this pool chain. If there is not enough memory, it is also swapped out into secondary memory in the sleep space. Okay. And then here comes your context switching. So what is context switching? So suppose you are running in your if you are in your running phase, and the uh, suddenly your CPU realizes, OS realizes that no, now you cannot run this process. There is a bigger process that you have to run. So what your OS does, it puts it into a state called preempted state, which is quite similar to ready state. Let's say it is quite similar to your ready state. So in most OS, these are quite common. So that is why it is a dotted line is there. So the context is saved in your stacks, the stack which we discussed, and then it returns to user running state when it is done. That high priority process has been executed, it returns back. So this is your structure of a process. So your main confusion was where the ready process or remain. It remains in both places. It remains in main memory and secondary memory. It depends upon how much memory is there in your system. Anything?
There two things were discussed for that process which is running. There were like two things. One is that the quantum unit of time each process gets,
Yeah.
and the second was the input output
Yeah.
event when occurs.
Yeah.
So that interrupt that is given in
One.
that diagram.
Yeah, yeah, 1 minute.
I- yeah. So the interrupt is because of what? Is it because of that time that they have been allotted goes beyond it, or what? Like that is
Yeah,
the
yeah, yeah, yeah. Both,
interruption.
both, both.
Both
Yeah.
or one.
Uh, so it goes from running to ready state only during the thing called context switch. So context switch happens in both cases. So suppose you are running so you are running the process and it is becoming timeout. So it has been running for a long time. In that case, a context switch occurs, as well as when a high priority process arrives. Those kind of things. So both cases it happens. One of the main this diagram this state diagram is basically very little bit smaller. So one of the main understanding of uh, the complete procedure is done through this diagram. So I will share this today. I will share this with the slides that I have, so you can go through it. So these also have an explanation for each of them, so you can read it. This state transition and all. So main class is, so this happens two things. So this, going back to the ready queue which we are saying due to interrupt and all, it happens mostly through this route, preemption. That is, it either it is been timed out, or uh, it has been interrupted for running a higher order process. Yeah, Sneha.
Uh, Clear that you told that in the context switching, we
Huh.
had learned that there is a hardware device called timer, which will allot that time and
Yeah,
then
yeah, yeah. Every
yeah.
process is allocated with a time.
But then, how does the CPU prioritize code? Like you are saying, high priority. What is that identity which makes a certain process of higher priority than the
Yeah, yeah.
other?
Okay, okay. Uh, See, everything has to be associated with some priority, right? So it is done through a queue, priority queue. Okay. So so you are asking me what is a priority. So every thing has a priority. Like in let's say you have you have a certain budget in your hand. Let's say 1,000 rupees. Now you will buy your essentials first, right? This is your priority instead of buying some other stuff and all. So that is how priority happens in also in case of OS. Something which is very urgent to be run, that is completed first, then other processes are run.
Yeah, so that is the priority queue.
Yeah, there is a priority queue. So when we will be going through the scheduling portion in the maybe in the next class and all, so you will see there are lots of scheduling options. So first come first serve, longest waiting time first. Then there is this priority queue thing, so where each processes have some kind of priority associated with it, and based on that it is being run. Okay, so I will share this part of the portion also. So this you can read it. So there is 1 or 2 page of explanation there. So you can read it and you can understand it again. Okay. So let's come back to this slide. Now let's we need to understand what is this process control block. So the process control block, consider it like a table. Okay. So so there is a table. Say let's say process table, and each let me just draw it once. So here let's say you have a table. So let's say it's called P table. So each entry corresponds to a process. So this is for one process, this is for another 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 process. Fine. Now, so this entry is basically called a PCB, process control block. And here is your content of this PCB. So there is your process state. So let's recall that state diagram. So this state diagram, so typically it also have this kind of process state. So in which state it is there, ready or running or waiting or terminated or new. So that status is being stored here. Then there is the program counter, location of the instruction to the next to execute. As I said, that your programs are basically consist of specific lines of codes that are stored in your main memory. It has the process needs to get it from that main memory and then execute it one by one. So that's why program counter is required. Then you have the CPU registers, content of all. So certain processes, let's say, are using some registers of the CPU, that which registers are being currently used are being stored. So why you need to store which CPU registers are currently being used? Because there are not only one processes, there are multiple processes, and everyone wants to use some kind of register. So that's why it needs to hold accountability of which registers are currently being used or not. So PCB contains each each block that represents the PCB contains the CPU registers that process is using. Then you have the scheduling information, the priorities, the scheduling key pointers that I was discussing, that each process has to be associated with a priority. Based on that priority, OS decides whether it has to be scheduled or not, when it has to schedule or not, whether it has at all has to be scheduled or not. Those kind of things they define it. I'm not remembering a good example from where I can give you the idea of why scheduling occurs and why that thing occurs. Let's say a firewall. So every OS has a firewall, right? So let's say your suddenly your OS needs to do a firewall checking that is important because of its security, but at the same time it was performing some other job. So at a time it has it does the scheduling of that let's say that firewall check before then executing any other process. Generally, there are CPU has multiple processes running at the same time. So generally, nobody cares. Like in human eye, you will not be able to understand how fast the scheduling occurs and all. It's quite vague to understand just like that. Like when and where the scheduling is occurring, CPU schedules it because it is very fast. Memory management information. So basically, like you have done some kind of malloc and calloc, and you have been allocated some memory from the heap. So the OS needs to remember so which are the portions of the memory it has currently being used by the process itself. So that is also another entry your PCB. Accounting information, CPU use, clock time elapsed and all. So it's quite understandable what is clock time elapsed and all. So when the process started, how much time it has gone from that time it has started, time limits and all, like how much longer it can run. Those kind of things are present in this accounting information. Then there is IO status information. IO devices to the process, a list of file opens. So let's say there are so you have opened the same like more than one for let's say you have written a C code and it's currently are using two files, or file 1 and file 2, and then you have another C code you have written which accesses file F2 and F3, F2 and F3. So F2 is being used by both the programs. So the OS needs to remember which file has been opened using which schedule and all. Those kind of things, which file like what kind of addition into the file they are doing, so what kind of deletion from the file they are doing. So those kind of IO status information has to be maintained by your OS. So it was also present in your program control block. So any doubt regarding this PCB and how it happens? Yeah,
Yeah, I did not understand where is this PCB located. Like when there is a scheduling done for a process in the running
yeah,
stage, whether the CPU takes the process, because process also has its own structure like heap and stack,
yeah, yeah.
and
Let me come to that. Okay. So here is something called P-table that is maintained across the OS. Okay. So it is not a part that is common to one process. It is common to all the processes. Okay. So each P-table has an entry. That is basically your PCB. So basically, this is a table, and its contents are basically the PCB. So PCB accounts for your ID number, your files opened, your priority, your time max allocated, and other things, right, which we discussed 2 minutes back. So this is your PCB and this is your P table. Now you are asking, where does this heap, stack and all comes from? There is another table that is maintained called U area. So that table maintains that. So let's for the timing think that it is something which is known to your process and it is present in your PCB. So it is present in your PCB, that information also. But those kind of things are present in your U area, that where is the heap located, how and that is then connected to your P table. I haven't seen the term U area here, but again I will say that you go back and read it. So there is this thing called P table and U area. Uh, Let me check if my lecture this part has that U area or not. So you see this process table has this state and its U area.
see.
Yeah, okay. So the field in the process table are as follows. There is a state and there is this U area. So U area is basically the location in the main memory on the secondary storage to locate the
Yeah.
process.
Have you shared some different?
Okay, okay, okay. 1 minute, 1 minute. So this is your state diagram, right? So 1 minute. So uh, so this part you understand, right? What is a P table and what is a PCB? Mm-hmm. So yeah,
Yes, yes.
yeah. So your question is where does this heap lie, right?
No, my question is like when the process is taken from the main memory to the CPU,
Hmm.
does the P table which you are saying is universal, is it already present on the CPU or it
Yeah,
comes
it is
with?
universal. It knows where is the P table. It consults the P table for any this scheduling and all persons. So see, there is the OS and there is the hardware. That is your CPU. Who does the scheduling? Who does the scheduling?
Oh yes, yes.
OS. Okay, right. So to OS it knows the P table and its contents. This doesn't need to know. It just need to run it. It has to check whether the timer that has been given has elapsed or not, and then it returns. Right. This is the factor. So that is rotated. Another. So you want to ask that. Uh, so you have seen this diagram when I said uh, that's ready to run in the memory. This process is in main memory. This is the swapped out memory, right? So so don't you think the OS needs to know where is the process present, whether is it in memory or secondary main memory or secondary memory? It needs to know, right, where the process is present. So you understand that the process is a structure basically. So basically it has those stacks, those queues, that heaps and all, those code portion, the stack portion and all.
Yeah.
Yeah. So basically it has some kind of memory and it has to be present somewhere, right? So we talked
Yeah.
about this that when it is ready to run, there is enough memory. It is in main memory, else it is in secondary memory, right? So consider. You consider your process is in your main memory. Obviously, so your process is suppose in this location, let's say 0x7815, and here is your process P1. So P1 is located, let's say, here. So your OS needs to know where is the process P1, right? It needs to know. So that information where the process is also kept in this PCB, also kept in this PCB. Okay. So that is a special area which is called U area. That is the place your like information is stored where the process is. So in a way, everything is present in the P table for the operating system to know what is my process, what is my priority, what is its priority, what is its time, where is it located, everything.
Yeah. That's true.
So so I will give you this I will with today's lecture I will give you this text. So it's a very good book and you can go through this text once and check it, like what are the things a state has, uh, so what process table has, and where is your process stored, all those things. Okay. Let's come back to our slides. So your PCB has your process state, counter, register, scheduling information, IO status information, and all that you might know. Let's come to the threads. So you know that one process. So thread is a unit of execution in CPU. So one process can have more than one thread. One process can only one thread also. So so just to mitigate or let's say parallelly work on in a single process, we use the concept called thread. So this thread will be covered in the next chapter in a much more detail. So we'll come back to threads again. So this is how process is represented in a Linux. You have your PID, you have your state, you have your time slice, mm, process parent and child. So uh, obviously the process is created by someone, like someone has to create a process. It is not just like that. Let's say uh, when you are running your Word, Microsoft Word, so the parent process opens the file, and that file is basically is currently the child process that is even like running through the file. Okay, so I mean to say like this. So so you have your MS Word, right? So so you start this application. So it runs the application. So it creates P1. Now you said open a file. So you tell P1 to open a file. So it turns let's say it creates a child P2 in which you are using this editing the file. Okay, now at the same time you want to open another file. What you do in that case is the it forks it creates another process. So basically P1 is creating P2. So P1 is called the parent process and P2 is the child process. So for P1, P2 is its child, and for P2, P1 is its parent. Okay, so this is the concept of creating a process and why creating why processes are created. So basically, this is a very simplistic example. I don't think Windows Word works like this, but Google Chrome works like this. Is that you see when multiple tabs are open, this kind of you will go beyond and check there are multiple processes are created accordingly. So in a way, Google Chrome works like this. But this is a very simplistic example of a child and parent processes and all. So for it is the process of creating a child process. Let's not use the term process. The method to create a process is called fork. So this is a example of child and parent processes. Next you have is uh, your list of so your parent process number, you have list of the children you have spammed, then you have your files which you have opened, this process has opened, and then the address space, like that I said, that where it is present in the main memory. So that is called basically the U area, but let's not use the term now. Maybe we will come back to it, but the term is basically U area. That is the struct asterisk n. So any doubt regarding this structure? So basically this is your PCB. So you know what is a like table, right? You a hash table that you know. So this is basically an entry of that hash table in context of processes. So any doubt regarding this? Okay, so let's go to the next slide. This is process scheduling. So the aim of the process scheduling is to uh, have the less time sharing and all. So processes gives up the CPU under two conditions, like IO request. So let's say IO request comes and either a timer has elapsed. So once a process gives up the CPU, it is added to the ready queue. So it comes back to the ready queue. Let's jump back to the diagram. Uh, so once its IO is done, is come back to the ready queue, and also it's case of an interrupt, it's come back to the ready queue. The process scheduler is a special program which selects among the available processes in the ready queue for the next execution on the CPU. So any doubt regarding this? So scheduling queues. So basically there are a few queues that are there for the processes. So one, you have your job queue. So set of all processes in the system. Ready queue, the processes that are in the main memory, ready and waiting to execute. And device queue, set of processes that are waiting for IO device. So basically here is your job queue. So in the new portion, there is your job queue. Here is your ready queue, and here is your IO queue. Okay, so here are the three queues present. So here is your job queue, here is your ready queue, and here is your IO queue. Next, now next, basically this ready queue and various IO devices are basically in your these are basically a queue. So queue are basically a list. So basically it needs to know the first and the last, which one is the next in the queue, and those kind of things. So here is your one is one key example of your process scheduling, how it happens. Here is your ready queue, CPU, IO request and all those kind of things. Forking a child, waiting for an interrupt, then being added to the ready queue every time. So the CPU, then from the ready queue it goes to the CPU. So IO request, it comes back to the ready queue. Time slice expired, basically it comes back to the ready queue. Forks a child, it comes back to the ready queue. Waiting for an interrupt occurs, it comes back to the ready queue. So it's quite open, like how it happens. So then this is the switching process, or let's say the context switch. So save the state in the PCB, reload from the PCB. So here is process executing. Uh, then there is a, let's say, a system call happens, so it or an interrupt happens or timeout happens. So it save the state into the PCB. Then it again reload from the PCB. Similarly, again it saves into the PCB and reloads from the PCB after executing P1. This is being discussed here. So basically here, what happens here is uh, uh, so P1 is there is a system call or interrupt, or let's say IO work. So it saves its context to the PCB 0. Now it wants to execute P1, so it reloads the state from PCB 1, is executed, then it saves into PCB 2, PCB 1, and then again reloads the PCB 0. So this is the full circle of using the context block. So this any doubt, this is a critical part. Then you have your schedulers, long-term schedulers, short-term schedulers, and IO schedulers. So let's come back to this diagram. So admitting from here to here is a long-term scheduling. So this from new state to ready state is your long-term scheduling. This ready to running state is your short-term scheduling, and this is your IO scheduling. These are the three types of scheduling. So always remember, new to ready is your long-term scheduling, ready to running is your short-term scheduling, and this running to, let's say, for IO and all, these are your IO scheduling. So so long-term scheduler, the why the like uh, the term long-term schedule is used, and it is a short-term schedule. The objective is that it depends on how many time it takes. So a long-term scheduler thing is so you remember that that is a very crucial point. So why I will bring a job into the main memory? Why I will bring a process into the main memory? Only when there is left, there is space available. So it doesn't happen quite often. It takes a time, let's say seconds and minutes. Whereas this CPU scheduling happens like in milliseconds. So that's why it is short and fast. That's why the name comes from. Okay, so any doubt regarding schedulers? So if I so if I come back to this. So this should be this thing. So to go from here to here or here to here, this is your long-term scheduling. Whether I have to go to the main memory or I have to go to the secondary memory, that is your long-term scheduling. This is your short-term. This is your I/O scheduling, to go to sleep for I/O work and all. And this is your short-term scheduling. This rescheduling process. These to these to these and this. This is your short-term scheduling. So any doubt regarding scheduling? Okay, so let's go to the next slide. Now multitasking in mobile systems. So there are foreground processes, background processes. So like when you are using your YouTube and all, there are multiple processes that are running beyond that are communicating for various purposes. One, let's say, communicates for with your processor to run the video. Other operates with your like say display unit to display it. So there are many processes that are running beyond it. Context switch, like I said, the CPU switches from one process to another process. The system must save the state of the old process and load the saves from the new process. So that is why the PCB is the state is stored in the PCB, and when it is done, it is again loaded back from the PCB and all in the stack portion. Context in the process is represented in the PCB. Context switching is pure overhead. System does no useful work for switching and all. So let's come back here. Context. So there are three types of contexts there in for processes. So one is user level context. Two is register level context, and three, process level contexts. So remember, the term context is basically means a snapshot.
The editor is not shared.
Yeah, saying a snapshot of your PCB. So one you have your user level context, you have your register level context, and you have your process level context. So what is your user level context? So let's say your process text, or you can say the code portion, that is user level. Then the data area, in the sense your global variables. These are your user level contexts. Now in register level context, comes your program counter, your stack pointer, These are your register level contexts. So you see these are all part of your PCB, but these are various different level of context that are available. And then there is your process level context. Your, yeah, ask.
Sir, how program counter and stack program works?
Uh, Program counter and stack pointer. Okay, so let's, let me clear. Yeah. So program counter. So basically, whatever program you write, let's say you are adding two numbers in C++. So it basically comes down to your uh, machine level language, right? So in assembly language, let's say your assembly language, this comes down to this. Let's say you are taking a number A from memory location 100, you are taking B from memory location 200, and you are adding it into C, A plus B, and you are storing it into memory location 300, the value of C, right? So A, B and C are, let's say, registers. So this is your machine level code. So these instructions, these are also known as instructions. These instructions are basically stored in your main memory. So this, let's say this instruction is stored in your location 101. This is located in your location 1002, and this is your located in 1003, and this is located in your let's say 1004. So when the CPU executes these instructions one by one, it loads from these memory locations. So when let's say CPU is executing this, the program counter will point to the next instruction that will be executed by the CPU. So in this case, when CPU is executing 1001, program counter will point to this. So basically it is pointing to the next instruction that will be executed. Program counter clear?
Yes, sir.
Yeah. So now what is stack pointer? Good question. Stack pointer. What is stack pointer? No, I don't want to delete anything. So you know what is a stack, right? Stack, you remember, right? What is a stack?
No, sir.
You don't know stack? Okay. So stack is a data structure where uh, input is this side, like the first, let's say the first input is, let's say 20 is stored here, 30 is stored upon it, 40 is stored upon it, and 50 is stored upon it. So natural logic is what, that we will print, that it gets printed from here, right? So 20 was printed, was inserted first, so 20 will be printed first, then 30 will be printed, then 40 will be printed, then 50 will be printed. But in stack what happens, you have to get the output from the top. So the first output will be 50, 40,
50.
30 and 20. So this concept is called uh, uh, LIFO, last in first out.
Sir, it is work like automata theory or something?
Yeah, in automata theory you have used stack, I think, for those Chomsky normal form.
Because we write type yeah, in first type 3,
Yeah, yeah.
right? First is type 3, then type 2, then type 1, then type 0. But we use type 0 firstly, right?
Yes.
Okay.
Yeah. So that is that. So uh, your CPU has this kind of stacks where it stores information uh, in when it does this context switching and all. So it needs to maintain the stack pointers, the stack in which from where it can get those data out. So so the stack pointer maintains basically this. The top is your stack pointer. Okay.
Okay.
Okay. So that is your context switching, and so I was describing what are the contexts. So you have your text, your data, and everything under your user level context. Then in register level context, you have your program counter and your stack pointer. And in the process level context, you have your process table entry. So that is basically your the table where the your context PCB is present. So that is your process level context. So these contexts are naturally saved when you are making a context switch. Then there are operation on processes. So this is a process creation chart. So process can be created and as well as destroyed. So in uh, uh, in uh, in your Linux, there is this fork command to do these processes. So this is a typical init and the init process creation thing. So once init is created, then login is created, Python is created, SSHID is created. Then the login creates more child process, bash creates ps and vim, SHD create TSH. So this is the process creation structure. This is the thing which happens when you are starting the system. So resource creation among the children and all, process and parent and children share all the resources. Uh, Children share subset of parent resources. Parents and children share no resources. This kind of relationship occurs. Uh, these are different instances that can happen. So one or the other can happen. So either parent and children share all resources, children share only a subset of parent resources, parent and children have no resources common. So another thing can be parent and children execute concurrently. Other thing can be parent waits until children terminates. So these are the different kinds of scenarios. Here is an example of yeah, Sneha.
I don't understand
Yeah.
how a certain process is decided being the child of a parent. Like in this diagram, the one which is
This one.
assigned
This one.
flowchart of the Unix code.
Oh,
Yeah. So like here, the bash comes under login.
no,
Like
not login, not login. Okay, don't think about like that. So,
then
so
it is showing
it is
the
not,
child.
like that. Okay, so init process creates this fork. So it creates this fork, it forks it, and then the login is created. Okay.
Is it with respect to time? Like if first login happens and then bash happens, then bash is the child of it.
Yeah. So let me just show it like this.
And if that
Yeah,
is
yeah.
true, then
1 minute. So basically your here is your init program, right? So
It is
init
now
program,
shared.
huh? Okay, okay, 1 minute. So this is your, so let's say init function. So here it first forks login, and so if you have seen the code, it will be like this: if chid is equals to for, uh, or let's say ch is equals to fork. So here they will write the login code. So what does this mean? So when you are doing a fork, it either returns a 0 or a child's id, right? So basically, uh, so when this init does this login fork, it uh, it creates the login process. So it will work on this. So basically, let me just clear this. Just,
Okay, so like
yeah, 1 minute,
the
1 minute. So so we have written. So let's say if fork not equals to 0. What does that mean? So this part of the code will be executed only by the child.
child.
Yes. So now this child is what? Login. So here the login code will be there. Understood?
Yeah.
Yeah. So this is how it happens. Or maybe so fork is one way of creating a process. Another way of creating a process is exeq. So what we'll do is the init process will start this login uh, application, login application from inside this init. That's how also a process is created.
But login is the child of init.
Uh, See, if you check this uh, thing, so it is called a tree of processes. Okay, so yeah, you can call it children and all, but technically it is not a children. But you can say that okay, like it is created by, yeah, it is a children. Yeah, sorry, it is a children. So if the main process get deleted, it doesn't matter. So this is how that happens. So processes can be created using these things. So either a system call which creates a new process, see, or a exe which basically used for that after the fork process replaces the memory space. So basically it creates a new process. Nothing this Java word you need to remember.
No, but they are like they in the lecture they told us that EXEC creates a child which has a new program, like it doesn't
Yeah,
duplicate the parents.
yeah,
Like
that's what I said, right? So here, here what happens is that once this exe login is created, it, it is not dependent on init. So init can work upon its own, exe can also work upon its own.
but EXE's exit will depend on because it has to return its termination to the phone.
Yeah, but see, these are one-time processes, this init and all, right? So that will not be a issue. So, so next week, let me. So I will provide you some good fork and. So yeah, it is part of the next week also, fork and exe practical codes. Okay, so I will prepare some codes that are very practically used to let you know how fork and exe works. I have seen later, next week there is exe or fork and exe, those things. Yeah. So a child is a duplicate of parent's address space. A child loads the program into the address space. Address space is basically its heap. No, not the heap, the PCB. So, so what a child do is, so, so here is your PCB. So what the when the fork happens, the child copies most of the things, and few things it prepares of its own, like the PID, right? That it has to be owned, but other part it copies the parent's PCB, and then designs it upon its own. Okay, so there is this address space funda is there, fundamentals, and here is a simple C program which is used to create a process. So here is your fork. So this part for basically it cannot create a new child. This part is executed by the child process, and this part is executed by the parent process. Okay. This wait is basically parents wait for the child to complete, but it is not necessary that the parent has to wait for the child to complete. Okay, any doubt?
Sir, can you get to the last slide?
Last slide.
Yes.
This one is the last slide.
No, sir. Before that.
Yeah.
Okay, thanks. Sir, can we have recording of this session?
Yeah, it is available in your NPTEL. You go to your NPTEL course and all, and there, like the code space, there you will see that problem solving session at the end. You can find it. Yeah, so let's quickly solve the problems for this week. And okay, so what is referred to as process control block? Control block, task controlling block.
See, task.
B, yeah, it is B. Task program control, process control. Process is basically a task, right? So that is it. Memory block and data block. So which of the following does a microkernel facilitate reliability, extensibility, and portability? Basically all of them. So microkernel uh, is basically small modules of your kernel. So it is easy to debug, extend to create a new kernel, or port it into someplace else. So that is your use for microkernel facility. Next, what does the fork call return?
The folks.
So what does the fork return? So the fork returns your, I mean, come on, you know what is this fork return? What is the answer? So what does the fork return? So the fork returns two things, 0 and process ID of the child. So to parent, it sends the process ID of the child, and the child it sends 0. PID of child to parent and 0 to child.
Sure.
Next you have which of the following is not true. Process scheduler selects among the available processes in the ready queue. Time sharing of the methods minimizes the CPU usage, and process gives up the CPU when an IO request comes. So,
Okay.
this
Well,
one,
which of the following is
this
not true?
this one
Sorry.
is true. So, process scheduler is the one which selects from ready to running. So the process scheduler selects which one of the jobs to select, which one of the process to select to the running queue. So
Time sharing.
yeah, time sharing of the methods minimizes usage. That is not true. That is false,
Maximizes.
because it may sometime minimize, may sometime not minimize. The process gives up the CPU when an IO request comes. True, because IO is a, so why does CPU give up, the process give up the CPU? The reason is CPU is very fast and IO is slow. So this IO request takes lot time. So for the process to hold on to the CPU doesn't make much sense. At that time, some other process can come and utilize the CPU. So let's say CPU takes 1 nanoseconds to process. IO operation takes 10 nanoseconds. So giving up the process CPU by the process actually helps. 9 other processes can come and use it. Then you have a list is referred to as dash is referred to as, this is used to keep track of the processes that are waiting to start and are located in the main memory.
Ready queue.
Why ready?
Because ready queue, the active processes are present in the main memory.
Yeah, correct. So so from new, and there is your ready, and then there is a running. So from the ready queue, the list of processes is present, and that has to be sent to this running place. So it will be ready queue. So what is short-term scheduler? So short-term scheduler is basically yeah. So basically
From
it's
ready to running.
ready to running. So this is a short-term scheduling. So it selects which process has to be executed next and allocate the CPU. So next is the critical difference between a short-term and long-term scheduler is,
Frequency.
yeah. So short-term, so long-term is basically adding uh, from new pool to ready pool. So this is a basically adding to the main memory. So this is a very lengthy process and it takes time. So the frequency will be less. And whereas the short term is basically from uh, uh, like ready to running, which is main memory to CPU, which is very like it takes much less time. So its frequency will be high. So that's why it is called short term. So it depends upon the frequency of execution. So next is, in regards to scheduler, which of the following claims is false? Short-term scheduler is faster than long-term scheduler. Uh, Next is long-term scheduler. So this is true. Short-term scheduler is faster than long-term scheduler. Long-term scheduler creates a good process mix. True, it creates new processes. Long-term scheduler responsible for process state transition from new to ready. That is also true. And short-term scheduler responsible for process state transition or waiting to ready. No, that is your I. Yeah, so that is this is false.
Oh,
So this job is of IO schedulers. This is not for short-term schedulers. It is for IO schedulers. Then you have only a dash. Only one process can execute at a time, while all processes are waiting for the processor. With this, more than one process are running simultaneously on. So this means is uniprocessor. This is your more than one process can be running. Section 9. So this is basically unit programming. Only one process runs at a time. So you have your program pre. So only one process P1 or program PRG and one process P1 is running at a time. So that is only one programming is running.
But you have told that each program has multiple
Yeah,
processes to it.
yeah. But let's see here it
When
says
we say that it is unit programming, then it means multiprocessing. By that logic, even C option
no 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 no
multiprocessing. Yeah.
no 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 no. See in the first case, oh, it's running at this time. So in the first case, it says only one process is executed at the same time. So that means only one program is being run. But
Yeah.
with multiprocessing, more than one process can be run simultaneously on the single node. So your question is why it is not uniprocessing multiprogramming, right?
My question is in the D option. Why is the first one uniprogramming? Why can't it be uniprocessing and
Yeah,
multiprocessing?
uniprocessing, there is no such term actually.
Yeah, so might not be there.
Yes.
That's what option.
So uniprogramming and multiprocessing, that is the term. Yeah. So let's come to the last one. So unique, each process is identified. So each process has its own.
Process.
Huh? So each process has its own process control block as well as process identifier. Both of them are correct. So each process has its own ID and it has to have a PCB that is stored in your P table. So today you read any textbook, you search for this term, P table or process table, as well as U area. Not covered in this part, but this is important. So this part you read. Okay. So last one is if a process fails, operating system write error information into. So we discussed log file. So operating system information is written to the log file. Okay. So that was the last question. Okay. So if you have any doubt, you can ask, or we'll meet again in the next week. I will send you all the these extra notes and this slide also in the meantime. Okay, so we'll again meet next week. Thank you for joining. Yeah,
Thank you, sir.
yeah, thank you.